And sometimes we want to train sparse model. Okay, the sparse model just means like the model is slimmer. There are a lot of connections with like zero weight. Okay, so that the computation can be done faster. Okay, which makes the sparse models better suited for the embedded systems. Okay, so if you want to train a model that to be more sparse, okay, one way to achieve that is to use like a strong L1, okay, L1 regularization, okay, which can sort of like get rid of like the connection with smaller weights, okay, and make those to be zero, okay, and you can also like train the model as usual and get rid of the tiny weights, okay, so manually set those tiny weights to be zero, okay, but if you do that, okay, although you can get a sparse model, it may degrade the model performance, okay, so as I said, using L1 regularization, okay, during training, okay, is a probably better way, okay, and another technique, okay, is the pruning technique that you can consider, okay. There are a lot of like pruning tools available, okay, which is called like a model optimization toolkit, or called TensorFlow, TFMOT, okay. This toolkit provides a lot of pruning API, which is able to iteratively remove connections during training based on their magnitude. So if you are interested in training a sparse model, so this is the TFMOT is something you can check out. Okay, we probably will not talk about this in this class, but I just want to give you a direction. Okay, that you can check out when you have more experience and you want to train a sparse model. Okay, and so far, okay, all the optimizers that we have covered, okay, are listed in this table, and basically, okay, we also list their convergence speed in general. Okay, of course, like the one with 3 stars normally means like they converge faster, but pretty much like momentum or NAG, they converge well, but not as fast as those like adaptive optimizers. Okay, not as fast. But in terms of the model quality after the training is done, okay, the non-adaptive optimization technique normally will give you a better. It will guarantee the model perform better. For error grade, as I already mentioned, it only works for very simple models, such as linear regression. Okay, for deep learning, we normally do not use error grade. Okay, but for RMS prob, ADAM, NADAM, ADAMX, okay, really, the model performance, okay, if you use them to train the model, it really depends on the data set. Okay, if the data set is not allergic to the adaptive optimization, then the model will normally perform well. Okay, and you get a fast convergence speed, which is nice. But on the other hand, if you get a model that is does not generalize very well, okay, then you may want to consider using either momentum or NAG to train a model. Okay, even though they are slower, but they will normally give you the model with a better performance. Okay. So then the next topic that we are going to cover today is the learning rate scheduling. Okay, so we know finding a good learning rate is important. I already talked about that earlier. So if you set it too high, training may diverge. If you set it too low, then it will take a long time to converge. Okay, if you set it slightly too high, you'll make progress very quickly at first, but it will end up dancing around the optimum. So, so you're not going to get a good performance. Okay, so unless you use adaptive learning rate optimization, so those adaptive optimization, as I said, they will adjust the learning rate, during the model training. So such as ELA grade, RMS prop, ADAM. Okay, so but even then it may take time to settle. Okay, so if you have a limited computing budget, so you may have to interrupt training before the converge, okay, happens. So you may result in a suboptimal solution. So here just to tell you, okay, we just want to tell you that learning rate is important. Okay, so here I just want to show you a figure that with the different learning curve. Okay, so when eta, the learning rate is too high, it might the model training may diverge. If the learning rate is good, you can see this orange line. Okay, sorry, if that's too small. Okay, learning rate too small, so it converges slowly. So it may take a long time to converge. Okay, so if your learning rate is just slightly too high, okay, what happens is that the model converge quickly initially, but you can see that it stays, the loss stays, high, okay, eventually. So we get a suboptimal solution because we may, the training may dance around in the optimal, around the optimal solution. So we don't get the optimal one. Okay. So this green line indicate, okay, you have exactly good learning rate. So you can see that, okay, it converges fast and it goes down to a very low loss, okay, which is very nice. But we know that it takes a lot of effort to find this right learning rate. So here we want to ask a question: is there a good way that we, first we want to quickly find, a way, okay, to set the learning rate so that it converge, and second, okay, it converge well. Not only that, the second, we want it to be, even faster. We want the converge to happen to be even faster than the best learning rate. Is it possible? Yes. You can see that if we use a slightly larger learning rate, so we are initially take this purple line, but after certain point, okay, we switch to a different learning rate, a lower learning rate. Okay, so what happens is that you can see eventually we have this dotted learning curve, and you can see this dotted learning curve may even perform, may perform even better than the best learning rate we can have. Okay, so this is like why we consider what we call like a learning rate scheduling. Okay, in the learning rate scheduling, basically we adaptively adjust the learning rate so that we would like to achieve something like this. Okay, we can dynamically change the learning rate so that it will normally, okay, normally, okay, this is not always the case, but normally we will start with a larger learning rate, but gradually shrink it, okay? That's the basic idea of like learning rate scheduling, okay? So, yeah, I think I went through this. So there are different learning rate schedules. Okay, here, okay, in this textbook, we are going to discuss 5 different scheduling. The first one is power scheduling. The second one is exponential scheduling. The third one is piecewise constant scheduling. The fourth one is performance scheduling. The last one is called one cycle scheduling. Okay, so we are going to go over all of these, okay, quickly. Okay, hopefully we can finish this topic today. Okay, the first one is called power scheduling. Okay, the idea, the formula that we use is something like this. Okay, so eta is a function of t. So where this t represent the iteration number. Okay, so eta t is eta 0 divided by 1 plus t over s to the power of c. Okay, so you can see there are several hyperparameters here. The first one is eta 0. The second one is s. The third one is c. Oh, t is not a hyperparameter, okay, because t represents number of iterations. Okay, so c is normally set to be 1. Okay, so we normally do not adjust this c. Okay, and this formula basically, okay, when c is 1, it basically just means like, okay, at the very beginning, the learning rate is eta 0. After s number of iteration, the learning rate is cut into half. Okay, eta 0 divided by 2. And after another s iterations, it becomes eta 0 divided by 3. Okay, and so on. So you can imagine, okay, every s iteration, okay, the eta 0, I mean, the denominator value increased by 1, right? So you can see that, okay, the learning rate actually reduce slower and slower here, right? Okay, so this is what we call power scheduling. Okay, so of course, I mean, we need to find a good value for eta 0 and the s. Okay, possibly c, but we normally do not adjust the c here. Okay, so even though it is named power scheduling, in reality, the learning rate reduced really slow. Okay, learning rate reduced really slow. It's not as powerful as you may think. Okay, so the second one is called exponential scheduling. Okay, and basically, okay, it's going to be eta t going to be eta 0 times 0.1 to the power t divided by s. So in this formula, you can see that every s iteration, the learning rate is reduced by 10 times, right? Every s iteration, the learning rate is reduced by 10 times. And this reduction rate remains the same, right? For every s iterations. Okay, every s iteration is reduced by 10 times. Every s iteration is reduced by 10 times. So this reduction, okay, is actually very, very fast. Okay, this is called exponential scheduling because, well, the learning rate reduction happens exponentially. Okay. The third one is called piecewise constant scheduling. This is very, very simple. Basically, it's just like every couple of epochs, okay, we change the learning rate to a certain number. Okay, so for example, okay, eta 0 to be 0.1 for the first 5 epochs. Then we change to a smaller one, such as 0.001 for the next 50 epochs, and so on. Okay, so this is piecewise constant scheduling. Okay, so if you compare the piecewise constant scheduling, you will see that it requires us to find out not only the right sequence of learning rates, but also how long each learning rate, okay, value will be used. Okay, how many iterations, how many epochs each learning rate will be used. So we end up need to find like a lot of, there are a lot of hyperparameters that we need to consider in the piecewise constant scheduling. Okay, so to be honest, this is actually not that easy to decide. Okay, because originally our issue is to find the optimal learning rate, right? Now we need to find a lot of good values. So this is actually not that helpful. Okay, actually. Okay, the first one is called performance scheduling. Okay, performance scheduling is kind of like remember the early stop. Early stop. What is early stop? Do you guys still remember? Basically, we use like the validation error, right? If the validation error do not reduce for a certain number of epochs, we stop the training, right? So the performance scheduling basically is similar. Okay, if the validation error does not go down for certain number of epochs, then we reduce the learning rate. Okay, the only difference is between the early stop and this performance scheduling is that, okay, is the action that is taken. Okay, the early stop, if validation error does not go down, okay, for the patient's number of epoch, we cut it. We just stop the training. But here we just reduce the learning rate normally by half. But you can basically by a factor of lambda. Okay, in general by a factor of lambda. So the last one is called one cycle scheduling. Okay, this one cycle scheduling is kind of complicated. Okay, which is actually proposed in 2018 paper by Leslie Smith. Okay, so this one cycle scheduling starts by increasing the initial learning rate. Okay, eta 0, growing linearly up to eta 1. Okay, again during the second half of training. Halfway through the training. Okay, then decrease the learning rate linearly again down to eta 0. Again during the second half of training, finishing the last few epochs by dropping the rate down by several order of magnitude, still linearly. Okay, then the maximum learning rate eta 1 is chosen using the same approach we use to find the optimal learning rate, and the initial learning rate eta 0 is roughly 10 times lower. Okay, so basically, okay, eta 1 is normally the optimal learning rate, but eta 0 is 10 times lower. So you can see that we start from a lower learning rate and growing linearly to the optimal learning rate, and then going down to the lower learning rate again. Okay, so this approach is kind of strange. Okay, kind of strange. And also, okay, when we use the momentum, okay, optimization with this one cycle scheduling, then we start with a high momentum, then drop down to a lower momentum. Okay, so there are a lot of small things that you need to consider in this approach. But even though, okay, I would say this is complicated. Okay, this is complicated. Okay, but the Leslie Smith, okay, did many experiments to show that this approach, okay, is able to speed up the training considerably and reach better performance. Okay, for example, okay, on like a CFAR 10 image database data set. Okay, this CFAR 10 image data set is again one famous image data set that is used for one competition. Okay, and this approach, this one cycle scheduling, okay, reaches 91.9 validation accuracy, okay, in just 100 epochs, okay. But if you use like a standard approach, it requires 800 epochs, and the accuracy is only 90.3%. So you can see that it's you know, even though this increase, okay, 1.6% is considered significant because the accuracy is already above 90%, right? So 1.6% is considered big, okay? And also, you know, this number of epochs for the training reduce 8 times, right? 8 times. So this is you know, they show that this is good, but to be honest with you, okay, this approach is kind of complicated, okay? It's complicated. So what should I say? I mean, I probably wouldn't recommend you, okay? They are you know, the exponential scheduling is perhaps like the easiest one, and you can get pretty good performance already, okay? And you know, it also has fewer hyperparameters to tune, okay, for exponential scheduling, okay? So a 2013 paper by Andres Senior, okay, of course, in 2013, you can imagine, one cycle scheduling wasn't proposed, right? One cycle scheduling was proposed in 2018. So in 2013, okay, only the other 4 scheduling was considered in this paper, okay? And they compare the performance of some of the most popular learning schedules when using momentum optimization to train DNN for speech recognition. And the conclusion is that, okay, both performance scheduling and the exponential scheduling perform well. So they favor exponential scheduling because it was easy to tune, and they converge slightly faster than optimal solution to the optimal solution. So they also mentioned that it was easier to implement than performance scheduling. But Keras has, you know, in Keras you don't need to worry about implementation. I mean, they are I mean, both very easy to set up. Okay, so the one cycle approach seemed to perform even better. But even when we say that, as I said, okay, one cycle scheduling, it may have a better performance, but it's complicated. You may want to really like study a little bit more before you use one cycle scheduling. Okay, so for the implementation, okay, the power and the exponential scheduling in Keras is very easy. Okay, for example, to implement the power scheduling, okay, just set the decay hyperparameter, okay, when creating optimizer. Okay, for example, here, SGD, and we set dk to be 10 to the power of -4. Okay, the dk basically is the inverse of s. Remember, s represent like how many steps is required to increase the denominator by 1. Remember? Okay, in the power scheduling, and here if we set the dk to be 10 to the power of -4, that means that s value is the inverse of this, which is like 10,000. Okay, 10,000. Okay, 10 to the power of 4. Okay, pretty much. Okay, so if you want like to use different s value, of course you can set dk. I mean, in different value. Okay, so Keras assume that c is equal to 1. As I said, like I mean, in power scheduling, we normally assume c to be 1. Okay, for exponential scheduling and piecewise scheduling, okay, they are quite simple to too. Okay, but of course we need to first define a function. Okay, which takes the current epoch and returns the learning rate. So, for example, for exponential decay, okay, we define this exponential decay function, okay, which takes the epoch. So it will return 0.01 times, this 0.01 means that eta 0, right? Eta 0 times this 0.1 to the power of epoch divided by 20. So every 20 epochs, we are going to reduce the learning rate by 10 times. So we first create this function. Okay, if you do not want to hard code the eta 0 and s, then you can create a function something like this to make eta 0 and s to be the parameter, okay, for this function. But well, you get an idea. I mean, this is pretty much like easy. Okay, very simple. Okay, just like implement. This is just like an implementation of the function in not in Keras, but in Python. Okay, so I don't think I need to go into detail for this. Okay, so and then with this function, okay, we create a learning rate scheduler callback. We give this callback that scheduling function and pass this callback to fit method. Okay, so it's something like this. Learning rate scheduler object to be this callback, learning rate scheduler, and we pass this function here. Okay, and then in the fit, when we call fit, okay, to train the model, we pass this LR scheduler, okay, as one of the callbacks. Okay, and that's it. Okay, so pretty much it's going to the learning rate scheduler will adjust the learning rate, okay, at the beginning of each epoch automatically. Okay, if you want to this learning rate to be updated more often, okay, for example at every step, then you can write your own callback. I think I talked about like how you can write your own callback earlier, right? Okay, we have like a control, like for example, at the beginning of the epoch, at end of epoch, at the beginning of iteration, at end of the iteration, a lot of this like a control for the callback. Okay, you can write your program by yourself. Okay, so in we even have like exponential scheduling. Section of the notebook. Okay, that is provided by the textbook, and you can check out. Okay. So updating the learning rate at every step makes sense if there are many steps per epoch. Okay, so it depends on your setting pretty much. So alternatively, you can use the keras.optimizers.schedules approach, okay, to do that. But we'll describe later. Okay, so the schedule function can optionally take the current learning rate as a second argument. Okay, so for example, okay, here, okay, we define the exponential decay function, okay, similar to the previous one. Okay, so this implementation relies on the optimizer's initial learning rate. Okay, but I think that this is like quite detail. Okay. So when you save a model, this is important. When you save a model, okay, you save like pretty much the optimizer and the learning rate will also get saved. Okay, but the epoch, okay, for example, say you train this model for 100 epochs already. Okay, so everything will be saved, but the number of epochs will not be saved. So if you restore this model and then you want to train it again, the epoch number will start from 1. Okay, but remember, in our implementation, a lot of like this learning rate scheduling, okay, depends on the number of epoch, right? So if the epoch starts from 1 again, you are going to use a large learning rate, right? And this model is already well trained, right? At least you have trained for maybe 100 epoch already, right? So you don't want to use like the large learning rate anymore, right? To train this, to continue training this model, right? So what you do is that, okay, you know, you want to, you know, when you train it, like when you restore this model, I mean, if you want to train it from, say, like 101 epoch, then you can use like a initial epoch argument, okay, in the fit method to specify, oh, this is 101 epoch, okay, so that those learning rate schedule knows that, oh, this is the 100